Streaming now. Welcome to BC Calculus. Welcome everybody who lives and exists in the abyss. Welcome to reality, or what we believe to be reality. Okay, one of the things I'm going to use is this real cool app. I would strongly encourage you to get it. It's free.
What is it?
It is called Desmos. Okay, so one of the things you can do with this, what?
No freaking way, dude.
What?
Sponsor?
What?
Sponsored by Desmos.
Yeah, okay, I don't have a sponsor, but that's a great idea. So, if you take a look on here, it gives you a Cartesian coordinate system. And if I click on this thing that looks like a wrench, one of the things I could do is I could change it to a polar curve. Okay? And it gives you the angle measures and all that stuff. And so that's one of the things I would encourage you to do. And I'm going to put the two equations that I have on, what is it, number 14 you said we're looking at?
Yeah.
Okay? And we're looking at intersection points, is that right?
Yeah.
We do this on like your TI.
Yeah, I'm going to show you what it looks like on your TI. And I will also do it on a Casio. And I don't have 14 right in front of me. What's the equation? R equals...
1 plus cosine of theta and 1 minus cosine of theta.
So on Desmos, you can simply go to R.
So what you're saying is we can use this on a test?
I haven't decided. Maybe. And what is it again? Plus what?
1 plus cosine theta. Yeah.
And I just type in the word theta here, and that pops up.
I can't see.
Yeah.
Is there a way to adjust the camera?
Yeah, is it hard to see?
Yeah.
Yeah.
I think it turns the screen brightness down.
Yeah. Just turning your screen brightness down.
On my phone?
Yeah, just a little bit.
Okay, how do I do that?
Swipe down at the top.
All the way to the top. All down.
No, go from the bottom.
Drag it down.
Yeah, why would you go top?
Spot.
Thank you. Does
Oh,
that
there-
work?
Yeah, you forgot the 1 though. It's 1 plus cosine theta.
Maybe this will be my new favorite app.
Personally, I like Boggle. Have they ever come up with
Okay, so when I type in theta, then I have it in there, and it should graph it, and there it is graphed. And you can see it's a cardioid, right? So I will ask you on the quiz, I'll give you some pictures, and you have to identify a cardioid, rows, and a circle. Okay? And so you're going to have on a test part that you have to use that is calculator and part that is no calculator. Okay, so you have to be able to graph it with no calculator.
When is this test?
All right. What's the other equation?
1 minus
1 minus
cosine theta?
cosine theta.
Why'd you say wig? Oh, if you're awake.
That's like thought.
Okay, so there are the two curves, and it looks like it has what?
You want?
How many intersection points?
3 or 3.
Okay, where are the 3? One on the top here, one on the bottom here, and it looks like there's one in the middle. So where X and where that spot is, right there in the middle of all those circles, that's called the origin, but it will also be referred to on the AP test as the pole. Okay, so the center of all those concentric circles, you'll see a lot of times be referred to as the pole. So the pole has it looks like it intersects there, correct? But it has a number of names. The radius is 0, but I could say 0 pi over 2, and it would be that spot, correct? Because you're not leaving and going out from that origin, right? Because r would be 0. So I could have any degree measure and be talking about that point. So what makes polar coordinates a little difficult is that we're going to do some of the same things to solve for them, but you're going to need a visual to say, all right, are they intersecting at the pole? That's one of the things we're going to take a look at today. Yes, ma'am.
Why do we do polar coordinates?
Because sometimes to be able to solve mathematical problems, it's a lot easier to leave the x and y coordinate system and explain it in a different type of system. So that's why we have parametric equations, that's why we have polar equations. So we can talk about the same shapes, like r equals 5 is a circle with a radius of 5, is a lot simpler to be able to compute than x squared plus y squared equals 25. Okay? Yep.
Okay, so like, why does pi like exist? Like, I know why pi exists for like circles and whatnot, but how did somebody find the number pi?
So what they, one of the basic shapes of geometry is a circle.
Yeah.
So you think of cultures, how many places they use a circle. And so they had measuring devices for a long, long time. The most common measuring device, at least in Egypt, and I think some Asian countries, is a rope that is knotted at unit lengths. Okay, and it's given a particular name, and I can't remember what it is. And so when they measured the circumference of a circle and measured the diameter of a circle, which for a lot of cultures were the two basic properties, they always noticed that no matter the size of the circle, when you take the circumference divided by the diameter, it was really close to the circumference being 3 times bigger. And so 3 became a very special number. And as, just saying, and as measurements get, and mathematics gets more complex dealing with measurement, they realize it's always a little bit more than that. Okay.
Is there like a number divided by another number that makes pi?
A lot of people use 22/7, and that's an estimation. Pi is an irrational number, which means it cannot be written in any rational form other than circumference divided by diameter. And in this class, we're going to prove that it's also an infinite series.
So you know how like a number divided by 9 is that number repeating?
Okay.
If you divide pi by 9, would that be like point pi repeating?
No, because it's an irrational number.
But like, because when you do it.
Okay, I had the same argument with a guy named Alex Martins. Do you know this argument?
Yeah, the
I was definitely going to
9.
ask you about it. So.
What was it, the 99% thing?
No,
That
it's
was
like
wrong.
when you take point pi. Can you just like write it out for us, Kruger? 'Cause
No.
it's definitely
No.
wrong. No. Okay, so like pi is like point pi would be like 3.14159 whatever. But then if you like add a 0 in front of it and then do like when you add it all up, I don't know. One sec. This is gonna take a while to write, but.
Yeah, can we talk about this at work time so I could finish up
Yeah.
these notes?
Yep. Yes, you can.
All right, so that's what it looks like on Desmos. And so what's nice is you get that coordinate system, all right? On a TI, I already got it in that form. What was it, 1 plus cosine theta? And 1 minus cosine theta? And so there's the graph right there of those two cardioids.
Students and staff should
Dang
move
it.
quickly to their
I left my Coke in my
Dude, Kruger, what's this water laced with, fam?
You're now
We all get
entering a
busted.
soft lockdown. All students and staff
This is
are
how-
in their assigned classroom
Actually, like,
Check your
You're
window.
all
Yeah,
You're now entering a sound lockdown.
What?
You can all go out into the
And I
forum to
can
go
write
pet the
it.
dogs.
This must have
What, Skinny?
yeah.
We are now entering
my-
the
Oh,
shut your mouth!
All students and staff should move quickly to their assigned classroom or location.
Definitely.
You're all north.
Just
been,
drug,
see, mine keeps
drogas.
sitting in a bunch of circles.
Drogas.
Surprisingly, just lock the door, turn the lights off.
We are
Drogas.
now entering the
Oh,
south lockdown.
I'm literally gonna
All
like
students and staff
Swallow
should move
swallow
to their
this
assigned
cat.
classroom.
What
Thank
drugs?
you.
You're all
John,
Hey.
Hi.
there are
Welcome
You the grapes are
So that's what it looks like on a TI. Are you able to figure out, you know, when you trace on a TI, and I don't know as much about TI as I do a Casio. So if I trace on that, and it can give me the ordered pair as I move around,
Yeah.
does it give you, it doesn't give you the slope, does it?
No.
Okay.
No.
You can like, how do you plug it?
Okay, so if I went to second calc, and I went to
DRD theta.
DRD theta,
Yeah, then you can find it.
and it'll give me that value of where I'm at.
Wow, what the heck?
Okay. And so what I'm doing is I'm giving, you still have to do these by hand, but it's an easy way to check your answers.
Like the time
On a Casio, it looks like this. What do I have? 1 plus cosine theta?
Yeah, and then one minus.
What if it's like 9?
So there are the graphs. Here when I trace, I turned on my derivative button. Yes, ma'am.
How do I, like, okay, so if I have something graphed like that, and I want to find, like, x equals 58, how do I type that in?
You hit trace?
Yeah, and then do what?
I don't know.
Wait, can you?
Go to
how did-
table.
How did you?
If
graph
I don't
that
want
on
to scroll
TI?
down to 58.
On a TI,
Put it in 5
Oh,
you got to go to mode and change it into polar
Oh,
coordinates.
that's what it is. Okay.
Oh,
Okay?
does connected have to be the dot?
All right, so I'm going to trace on this. And when I trace on this,
Can you move it down a little?
yeah, when I trace on this, you can see it's giving me the derivative too. So it's giving me drd theta dy
Yeah, what
dx.
do you use? What's DRD theta?
What do I use for what?
Or why, what's DRD theta? What do you use that for?
Well, we're knowing what the ordered pair is there, correct? Because r comma theta is our ordered pair on the polar coordinate. And this gives me what the slope of the tangent line would be in rectangular. And this is giving me the rate of change of the radius with respect to the angle measurement. Does that answer that? Okay. So the reason I bring those up are those are some methods in which you can use to check your answers. Okay? So let's take a look at the first one. And so I believe the graph looked like this.
That'd be fine, Abby. Just keep it in mind. Just keep in mind while you're getting that. It's better to be sure. Actually, if you know you
So if I look at the drawing, I can see it looks like it has 3 intersection points, correct? All right, so one of the things I'm going to do is, just like I do in Cartesian, when I'm looking for intersection points, I make those two equations equal to each other. And so when I solve this, I get 2 cosine theta is equal to 0. And so that means cosine theta is equal to 0, and cosine is equal to 0 at 2 spots, and those 2 spots are pi over 2 and 3 pi over 2. So I can check if I put pi over 2 into my function, I get a, in this function, I get, I get I get a 0 here, and I get 1 plus 0. And over here I get 1 minus 0, and so they both have a radius of 1, so they'll intersect here. And if I put 3 pi over 2, they both equal 1, so they intersect down here.
What about at the pole?
Oh, we're going to talk about the poles. A lot of times the pole won't show up because there'll be different names for the pole. Okay? And I was talking about that before. So all that needs to happen for a graph to be at the pole is that the radius is 0. Okay? So I'm going to let this equal 0. And that means -1 is going to equal at cosine of theta. And theta would be what? It would be pi. So this point where it's at the pole at 0 comma pi. Likewise, I could do the same thing with this equation. 0 equals 1 minus cosine theta. And so cosine theta is going to equal 1. So it's at the pole when? 2 pi or 0. So I could say it's for this one, at 0, 0. So do they intersect? Yeah, because there's two. Now, this is the same point, correct?
How is it the same point?
Oh, because we talked about this because it doesn't move. Yep.
Because right here's the pole, correct? If I asked you to plot that point, would you plot it here?
That makes sense.
If I asked you to plot that point, would you plot it here? You can have multiple names. In fact, for the pole, there's an infinite number of names you can give it, right?
Yes.
It's 0 comma whatever you want it to be.
Yes.
It's going to be that pole. And since both of those give me a point, they intersect at that point.
Yes.
Okay? So this 0, 0, that name, so here are the 3 points that I have. I have 1 comma pi over 2 and 1 comma 3 pi over 2. All right, number 15. So I could draw this one.
Do you just plug it back in to get the 1 on the other side?
Yes.
Yep.
Okay.
Yep. And so r equals cosine theta looks like this. That's supposed to be a circle.
It looks like an angle.
It doesn't look like a circle.
Yeah. It's a lightning bug.
And this one looks like this. So that's my graph. So you got a cardioid on this side, you got a circle on this side, and I'm going to zoom in. All right, so it looks like they have how many intersection points? 3. 1 here, 1 here, and 1 here. So it looks like they intersect at the pole again, correct? Something like that. So again, I'm going to let them equal to each other. So that 2 equals 4 cosine theta. 1/2 equals cosine theta. So theta has to be what when they're a half?
Pi over 4.
Pi over 4, the square root of 2 over 2. Pi over what? Pi over 3. Now notice, it's got to be positive, correct? Right? So pi over 3, and where else is cosine positive? The fourth quadrant, right? So what's that going to be? It's going to be something over 3. 5 pi over 3. Okay? So if I put pi over 3 in here, I get a half. And I have 2 minus 3 halves. Isn't that a half? And over here, whether I put pi over 3 or 3 pi over 3, I'm going to get a half also. So my 2 points are a half comma pi over 3 and a half comma 5 pi over 3. And then my question is, can I make r equal 0? Well, cosine is 0 when? Pi over 2 and 3 pi over 2. So at least I have one point in which that's the case, correct? And that's at the pole. It's at the origin. And so over here, can I make this equal to 0? Well, it would mean that I would have 2/3, correct? Equals the cosine of theta, right? And so I could go to my calculator to figure out what that angle measurement is, correct? And I got 0.841 radians. Did anybody else get that? Did you?
What'd you get?
I got 0.841 radians. Did other people get that? So 0, 0.841 radians. So I can say that they meet at the pole at 0, 0. I can give it any name I want. I might as well give it the simplest name.
But do you have to go through that process to prove that they can both be at 0 at one point?
If you didn't have a picture, which you know what I'm saying, if you didn't have the capability of drawing a graph, that's what I would do.
Well, since you drew that picture, if this was an AP question, would you have to do all that work, or could you just say at 0, 0 and then those 2 points?
They may ask you in this function or in this equation, where does it go to the pole? Okay? Now, if I take a look at these two graphs,
Doesn't look circular.
this one is a circle and this one is a circle. This is a circle that looks like this. That's this one. And the other one looks like this. They're not perfect, but would you agree that based on yesterday that this is the case? And I think this one's pretty obvious. If I'm always 2 units out and I can rotate any direction I want, I'm going to get a circle that looks like this. So they do not meet at the pole. In other words, there's no theta that I can get that's going to make R0 on this graph. So again, I can figure out where they intersect. Notice they're going to intersect in the first and second quadrants, correct? And I'm going to get 1/2 equals the sine of theta. Can I make that jump? And so theta's got to be equal to what? Pi over 6 and 5 pi over 6.
0 pi over 2.
And so my points are 1/2 comma pi over 6 and 1/2 5 pi over 6.
We are now in an all clear. We are now in an all clear from the soft lockdown drill.
Thanks for the clarification.
Thank you.
Okay, so I edited these notes, and that's why there was some confusion the other day about these notes. And this is something else I edited. And I think there's a lot of similarities with the derivative, just like there was with the parametric equations. And since you have to remember those, what I'm going to do is I'm going to make some modifications here. We know this is true. And we know that y equals our sine is, theta is true, correct? And usually r is written as like something is being done to theta, correct? So r is the dependent variable, theta is the independent variable. So I could actually say theta is computed, excuse me, r is computed by plugging theta into it, correct? All right, so what I'm going to do is I'm going to cross this out, and I'm going to write this as a function r theta. I think that's better because then you know it computes the radius. And likewise here, I'm going to cross that out, and I'm going to call, rather than f theta, I'm going to call it r theta. And I'm going to cross all of this out. Because I think it just makes it too confusing and way too much to remember. So I'm going to find the points of horizontal tangent line. All right, so when I have dy dx, or horizontal tangent line means I'm going to have 0 over some constant. Would you agree? Right? That gives me a slope of 0 if I want a horizontal tangent line. So the way dy dx is going to be computed, and I think this is going to make sense since we've already talked about parametric equations, it's going to be dx d theta, dy d theta over dx d theta. Is that making sense? Okay, so I'm going to have this equation. I'm going to say, okay, x is equal to r cosine theta. Y equals r sine theta. And if I'm just looking for horizontal tangents, I'm really only looking for where that is 0. Would you agree? So what I'm going to do then is say y is equal to, and if you notice r is equal to this, so I can say that I'm going to have 1 minus 3 times the sine of theta times the sine of theta. So now I'm going to take the derivative. Well, actually, I'm going to multiply this through it. I'm going to have the sine of theta minus 3 sine squared theta. Is that better? So now I'm going to take the derivative. And I'm going to get the cosine of theta minus 6 sine of theta cosine theta. And is that too big of a jump?
No.
I want a horizontal tangent line, so I'm going to make it equal to 0. I'm going to factor out a cosine. And I'm going to have 1 minus 6 sine of theta. I'm going to let the cosine of theta equal 0. And theta is going to be pi over 2 and 3 pi over 2. I'm going to let 1 minus 6, the sine of theta, equal to 0. And I'm going to get the sine of theta is equal to 1/6. That means the sine inverse of 1/6 is going to be my theta. And I got theta to be about 0.167. Okay, so now what I'm going to do is I'm going to check my answers. And I'm going to put in 1 minus 3 sine theta. Draw it. I'm going to make it a lot bigger. Alrighty, so it looks like there are 2 horizontal tangent lines here. Would you agree? Right?
Yep.
And it looks like there's a horizontal tangent line here. And a horizontal tangent line here, correct? So it looks like I should have 4 of them. I have 3 of them. I'll talk about that in a second. So what I'm going to do is I'm going to trace, and I'm going to first put in pi over 2. And if I take a look, dy dx is equal to 0 at that point. I'm going to trace again. And I'm going to put 3 pi over 2 in there. And you can see I have that. Okay? So the question is, where are these 2 coming from? Well, if I go back to this, there's that answer, correct? That's this spot.
Can you move that down, please?
That's this spot in the first quadrant, correct? How do I get this angle measurement in the first quadrant? Well, if you think about it, to get this point right here, I have 0.167 radians. And I want to get this point over here. Wouldn't this be a negative 0.167 radians going in this direction? So couldn't I say pi minus 0.167 to get to this angle right here? Is that making sense? All right, so what I'm going to do is I'm going to compute that, and I'm going to get that theta could also be 2.974. And that was pi minus 0.617 something. And so now I'm going to trace this, and I'm going to put in 0.167. There I am right there. You can see I'm not at 0, but I'm at a really small number, aren't I? That's because